Hello and welcome back. Let's talk about arc length. Common misconception by many students is that, say we had some random curve here going from some value A to B, is that the arc length would just be B minus A. You might be surprised to find out that it's not. You might not be surprised, but I'll do a little demonstration here. If I get this thing to cooperate, pin it down here, I pull it out with my fingers on B here, pull it out, it's actually much longer. We might find that not too surprising. You might find that very surprising. Fortunately, none of my markers want to work extremely well right now, but what if we wanted to find the arc length? Well, we'll call the arc length S. So we know that S equals the integral from A to B of ds, or just the integral of ds. We know that's going to equal S. Now we should keep in mind that as our function continues, S will continue, so this actually just gives us a function of how S continues as X does. So it's actually S of X. But we're not going to worry about that yet. So what is ds? Well, D is a small segment of our line here. Little tiny thing right in there. And what we can do is we can use the Pythagorean theorem with our right triangle with ds up here, dx down here, and dy up here, because there's a small increment of y and a small increment of x for every section of ds. So, what do we know now? Well, we know ds is the root of dx squared plus dy squared. Now, this is not something we've seen before, so let's simplify, or I guess not exactly simplify. Let's just make it look a little more normal. I'm going to do a little trick here. I'm going to times everything by dx over dx. Now I'm going to pull this dx over. I'm going to go 1 over dx times dx, and I'm going to bring this dx, or 1 over dx, inside of the root. So now I've got these expanded by a dx, or a 1 over dx squared, because remember you have to bring things inside. To bring things inside, you have to square them. So now we have ds equals root dx over dx squared plus dy over dx also squared dx, which makes this integral very, very possible to evaluate. Dx over dx, of course, is just 1. 1 squared is also just 1. So this is just 1 plus dy over dx squared with respect to x. So S is the integral of ds, which of course we just figured out is root 1 plus dy over dx squared dx. Boom. Now, these integrals can become very, very complicated to solve. So, I actually forgot my bounds of integration there. So, I might not end up solving the integral. I apologize, but we're going to need to get a bit more of intuition to figure out how to solve these types of integrals. So, actually, you know what? Yeah, I'll go through a little example, but it'll be a much simpler one that won't be much of a surprise to us. So let's take the graph y equals x. Well, our dy over dx is 1, so this gives us or let's integrate from 0 to, say, 5. We've got s equals integral from 0 to 5, root 1 plus, what's dy dx? 1 dx, which is just root 2 times 5 minus 0, which is 5 root 2. Let's confirm what we found. Well, we've actually just got 5 down here, 5 here. This is s as well. This entire length is. So s equals root 5 squared plus 5 squared equals root 50, which is root 25 times root 2, which is 5 root 2. Indeed, our formula works. We've done the correct derivation, and this will be very important for Calc 3. So if you plan on taking that at any point, get this into your head. Anyways, thanks for watching. I'll catch you in the next one.